Quadratics. Which I characterize as annoying but necessary. You know, I can't remember the last time I used a quadratic. I might have, you know, a lot of times, well, think of the article about family income and child education, right? We weren't sure what the relationship was. We could have fit a quadratic, but a quadratic doesn't make much sense because it's U-shaped, right? You know, you can do linear, you can do quadratic, you can do log linear, you can do dummy variables, various ways of describing relationships. And rarely in my experience is a quadratic the one to choose. But other people do. There are a lot of latent growth models that use quadratics. So we need to know what they're about. That's why I say it's annoying, but it's necessary. So let's start in. Quadratic, reaching back into algebra, is just y equals a plus b1x plus b2x squared. And that you could think of as the formula for the equation. There's going to be some kind of a U shape or inverted U shape, right? In our case, we've got books over here, and we've got test score here. And we think the quadratic might be inverted U. Test scores might increase at a decreasing rate. That's what this is all about. The slope is steeper here and gets smaller and smaller and smaller. It reaches some maximum. And then by its very nature, what a quadratic does is constrain this half of the curve to be exactly the same as this half of the curve, so it has to be totally symmetrical. And in this case, you know, it's absurd to think that this shape accurately describes the full distribution. But once you get beyond some number of books, you actually have a decline in test scores the more books you have. But the quadratic forces that relationship to be the case. So you might have most of the sample around here, which is the case for the ECLSK data set and the Fryer and Levitt study, but there's nothing going in that's going to guarantee that the bulk of the data are going to be over here. But anyway, that's the general form of the quadratic. It's useful because the slope is changing constantly as you go along the quadratic to know exactly what the formula for the slope is, right? And that slope is just going to be the derivative of this equation with respect to x. Constant drops out, you're going to get b1 plus the exponent times b2 and reduce the power of x down by 1. So it's going to be b1 plus b2x. That's the formula for the slope of the equation. So the formula for the equation itself, if I have books, plugging in a value of books equals 100, x equals 100, plug in 100 into x and 100 squared into x squared. If I know B1, B2, and A, then I know exactly what the position is on this curve. And so in that sense, this is the formula for the equation itself. This is the formula for the slope. So by the same token, if I plug in any value for x, let's say 100, if I know B1 and B2, I can tell you what the slope is at that point, x equals 100. All right, so one of the points of on the assignment this week fed directly from that fact. The slope is B1 plus B2 x2. So one of the questions was, what is the slope of the quadratic at x equals 0? Well, x equals 0, that drops out. So the slope at x equals 0 is just b1. Okay, that's the answer. And it turns out that that was 0.006. People got 0.006 in a variety of ways, but it's most obviously transparent by just finding what the slope of the equation is at a particular point. And that's just plugging x into the slope for the equation. Everybody see that? Any questions? Okay, so quadratic is either inverted U-shape or U-shape. What that means is that there is a point, either the maximum or the minimum, at which it's perfectly flat, slope is 0. So we can find that maximum minimum by just plugging into this formula for the slope. What's the x where the slope is 0? So 0 equals b1 plus 2b2x. And if you solve for x, the b1 comes over on this side, so it's minus b1, and you divide both sides by 2b2. So the maximum or minimum point is just minus b1 over 2b2. So if someone's estimating a quadratic, all you have to do is look at these two numbers, do this simple division, and it will tell you exactly where the maximum is or the minimum is. And then this other rule, if b2 is less than 0, then we have a inverted U shape. If b2 is greater than 0, then we have a U shape. All right, so first thing to look for is just what the sign of this is. Even though you suspect that there is this relationship between books and test scores are going to increase at a decreasing rate, and you fit a parabola, there's nothing that guarantees the parabola isn't going to look like that. Or that. All right, so the heart of the data is here. Well, if this is like 100 books, 200 books, the mean, if you look at the Pryor and Levitt article, is about 60. So the points are scattered around this 0 to 100. I'm sure there are a few observations that are more than 100, but it's mostly this kind of area in here. And the tricky thing about quadratic is you've got the points. It could be, well, all right. So let's take a real life example here. Remember that motivation data set that we talked about before? We had this task value as a function of age. And there's this, it's middle school kids, and what happens is motivation pretty much tanks during middle school. So you had this negative slope. Suppose you had two different kids. And here we have 10 to 15, let's say, ages 10 to 15, we're getting the middle school slope. Let's say we had one kid with a point here, a point here, a point here, and a point here. So it's declining, and it seems to be declining at an increasing rate. Right, that could happen. And for another child, you could have a decline that's declining at a decreasing rate. It's still declining, but it's the steepness is greatest here and it's flatter here. Up here, you're getting steeper as you go along. So think about fitting quadratics to those two kids. This is what latent growth models do sometimes. A quadratic fit to these points, because that's going down at an increasing rate. Think about the best U shape that's going to capture that. It's going to look like that, right? So these points are way out here. You know, no one's under age 10, but those points are going to drive what the position of the quadratic is. And it can only make a U shape, and it's just going to find the U shape where this part of the tail of the U fits to these data the best. But then look down here, same general pattern, but the decrease is at a decreasing rate. And the best quadratic here is going to look something like that, maybe. Right? So you've got two kids with very similar trajectories in terms of their motivation across middle school. If you describe them with a linear function, you're going to have very similar slopes, right? But if you fit a quadratic, you're kind of opening yourself up to this strange situation where in one case, you're getting this inverted U positioned over mostly to the left of the 0 point on age. In this other case, you're getting a U shape that's positioned mostly far to the right of the 0 to 15 age range. So if you, well, let's keep that in our minds. I want to return to this issue of latent growth models. But the point is, once you open it up to quadratics, the imposition of the symmetrical shape could produce very, very different kinds of parabolas for people who have data that might look pretty similar. There must be questions.
I have a question.
Sure.
So on the middle graph with the green line,
Right.
yeah. How would you know to fit a quadratic? Because anything under the age of 0 wouldn't logically make any sense. So wouldn't that mean you only look at like the downside of the curve and not the other side? So how would you still know to fit a quadratic then? It would just be like half of the quadratic.
Maybe I should do a little bit more on latent growth models. Latent growth models actually fit quadratics or linear functions or higher order functions to individuals based on very small numbers of observations, right? There's a level 1 where if it's quadratic, you've got test score, or in this case, sorry, task value is some function of age and age squared. And then there's a level 2 where you take each of these coefficients. So in other words, you fit this to every individual, and then every individual's constant gets is treated as a dependent variable here, and you might fit it as a function of let's say SES, maybe some school variable, like let's say dual language, curricula. So you explain the A's, you explain the B1s with all this, and you explain the B2s with all this. But the heart of it in the first stage is just fitting, in this case, a quadratic to every individual, right? And to say, how do you know to fit a quadratic? You don't know, but it's fancy to fit a quadratic. So you fit a quadratic. That's basically what's going on. And it might be, for books and test scores, a quadratic relationship is not unreasonable. It's not unreasonable for the sample as a whole, but it's probably unreasonable for any particular individual if somehow they had varying books over time. In this case, it might be that you basically have a downward trajectory that's fairly linear. You want to do a growth model to see what's predicting to the slope at the origin and the curvature. This is kind of a curvature parameter. So you fit a quadratic, but you get wildly different values for B1 and B2 depending upon how the quadratic fits in particular, right? So it's almost never the case that people know to fit a quadratic. It's often the case that they fit a quadratic because everyone else fits a quadratic, right? And they read about fitting a quadratic growth function. Growth is rarely perfectly linear. It often, especially if it's an achievement kind of measure, it's going to be more rapid at younger ages and it kind of tails off. So a quadratic kind of makes sense in the aggregate. But if you're fitting it at an individual level, anything goes. And you can easily, the program is just doing the best it can to fit to a very small number of data points if you're fitting this multi-level model. So you've got a negative B squared or B2 here for the green person. You've got a positive B2 here because it's a U shape, right? And you're mixing those positive and negatives in as dependent variables when you're trying to explain them by whatever independent variables of interest there are.
Greg, you might have said this already, but I just want to ask, so it's explicit, like why it's being used. Why did the study we've been doing in our homework use quadratic? What was the reason for that?
Yeah, it's a good question. People often, so books, if you think about the role of understanding the relationship between books and test scores in the Fryer and Levitt article, it's hardly relevant. It's relevant as a control variable. You want to know to what extent group differences remain after you control for a bunch of family background variables that are in the data set. So it's useful as one of those variables. I suspect what they did was to do some diagnostic work on the set of independent variables that they have. And it might have turned out that it looked like books, quadratic to books fit better than a non-quadratic, in which case they used a quadratic. But that they used a quadratic is almost completely irrelevant for the basic purpose of the article. It was just when you're throwing in a bunch of control variables, if things really aren't linear with the variable that you're throwing in, then you should put in some other form. You should put in dummy variables. You should put in a log linear relationship. You should put in maybe a quadratic, because the quadratic probably doesn't do that badly. As you know, or many of you know, now the peak is about 150 books. The mean is around 60. So the quadratic expression is significant, right? We'll take a closer look at this, but the standard error on the B2 is small relative to B2, so it's a significant nonlinear functional form. And in this particular case, you're really fitting this increasing at a decreasing rate portion of the parabola to the heart of the sample. So, you're doing a good job of describing that somewhat nonlinear relationship between number of books and test scores with a parabola. So it's probably, it's useful for that purpose. It was useful as an example in the assignment to kind of get you into thinking about quadratics. But in the context of the purpose of the article, it's playing a very minor role. Any other questions?
Excuse me, I have a question as well. So,
Sure.
So just like, can we say that we can give like a freedom degree of freedom to each variable, and like, for example, like have a degree of that polynomial that we're trying to find. For example, for the books, we have the freedom of 2. And like fit those lines or quadratics based on the variable, that freedom. And like, for example, if there isn't any quadratic relation between those two, then like the coefficient of our degree 2 would be like close to 0. Is this something that like happens in like applications?
Yeah, so those are good points. Degrees of freedom depend directly on the number of observations you've got, right? And if you have a really small data set, if you've got only 50 kids, let's say, it's degrees of freedom matter. You don't want to add in extra variables. One rule of thumb is that you should have at least 10 times as many observations as you have variables, right? So that kind of constrains the number of variables that you include if your sample size is small. In the case of Levitt and Fryer, it's thousands and thousands, so you're not really constrained that way. So that's your first point. But the second point is, you could think about putting in a quadratic, you could put a cubic, you could put a quartic. You could just keep adding, x cubed, x to the 4th, x to the 5th, and so forth. And that fits a more and more complicated curve that has the potential for fitting the data better. And indeed, with the quadratic, if you ask, is the quadratic worth it? You can do exactly what you say. You can make it linear, then you can add a quadratic. You can see whether the coefficient on the quadratic is significant or not. If it's not, you can drop it. That work is not completely unimportant, but it's completely secondary to most. Now, with any analysis, you've got a list of 10 problems. You want to rank it according to the biggest problem, the next biggest problem, the next biggest problem. And usually issues of causation are kind of toward the top. And what order your independent variables should be? Should they be squared, cubes, and so forth? That tends to be down number 9 or number 10. There are usually a lot of other bigger fish to fry, as you say, when going about trying to do an empirical analysis. But there's nothing wrong with going through the steps that you talked about. To say that if you put in a squared term and it turns out to be insignificant, that tells you it's not significantly parabolic, but there could be other nonlinear forms that it might take that a parabola really wouldn't be informative about, right? So it's a diagnostic, but it's not a very definitive diagnostic about whether the functional form is linear or not. If you want to be definitive, use dummy variables, right? Take your whole range of books in this case, divide the sample according to whether it's in the bottom 20% of books, the second 20%, the third 20%, and then estimate what that set of dummy variables looks like. That's, as we said, non-parametric. We're making no assumptions about the fact that it has to be U-shaped or inverted U-shaped, and it will sketch out, exactly what the functional form looks like. So you could really argue with your argument that it would be best if all independent variables were expressed as dummy variables, a bunch of dummy variables, because that would enable the model to come up with the best prediction of y in this case, because it allows any sort of functional form. As a practical matter, because these are 8th order concerned, most people just throw in linear variables, or they throw in variables and assume a linear relationship. And if there's some reason to think that, if it's a somewhat important variable, you might want to do investigating whether that's the case. If not, going with linear form is probably fine. You should be worried about up-against columns. Any other questions?
I have a question about the homework.
Yes.
So for the last question, we were supposed to draw the graph.
Right.
And I got the maximum point and y-intercept and then drew the graph, but I don't think I got it right. Is this supposed to look like the graph that you drew, the first one that you drew?
Yeah, so let's think about that. Let me share my screen here for a second. All right, so you should be able to see the Levitt and Fryer table 2, right? You were instructed to look to column 5, fall kindergarten math scores in this case. The equation was, I'll pick this up. The equation was math score is some constant let me just lump everything else into other stuff in order to concentrate on the minus 0.006 books, minus 0.021 books, I'm sorry, plus 006 books, minus 021, is that right?
Wasn't there supposed to be 3 more zeros?
Yeah. So that's coming up because that was confusing to some people. So the standard error here is 0.001, and the standard error on book squared is 0.002. Okay, so let me share again. And just make a few points about this table. So I like this table. This is a nice table. You know, as I've tried to say, you can't assume people are completely attentive to what you've written in the text before you get to the table. So the table should be as self-explanatory as possible. One nice thing, if you look at the labels over in the first column, they aren't variable labels. Some people put in variable labels, or they think that they can't use more than 7 or 8 characters for the label when you're labeling a variable. You know, you've got a word chart you can fill in, and you can make this first column as wide as possible in order to describe variables as completely as possible, right? So age in months, birth weight in ounces, mother over 30 at first birth. So there's no ambiguity as to what these variables are. And I would urge you, when you do tables on your own, to have these labels be as completely self-explanatory as possible. It's set up so that all of the coefficients have 3 decimal places, and the standard errors have 3 as well. You know, by and large, you want to have as few numbers on this table as possible. So, you know, having more than 3 significant digits is usually completely unnecessary. You know, if you have some coefficient that's, you know, let's say the coefficient's 0.2 and the confidence interval goes from 0 to 0.4. So you've got a pretty big confidence interval. And if you write the coefficient as 0.2054276, you know, which is what the output might say, that's an absurdly overly precise way of expressing it, right? You're not that sure that it's somewhere in between 0.1 and 0.3, right? The confidence interval goes between 0 and 0.4. So how can you have certainty that it's 2076452 or whatever I said? So just keep the significant digits to a minimum. 3 is usually enough. Sometimes 2 works okay. And all right, so another annoying thing. The nice thing about teaching is you can make clear all of your pet peeves. And one of my pet peeves is when people don't put trailing zeros in. Look at 0.11. All these others are 3 significant digits. Is that 0.110? Is it 0.114? You know, it probably happens, and this can happen when you transfer data in from Stata into a Excel file, is that if you haven't formatted the cells to be numbers, and you could easily lose these trailing zeros and leave the poor reader with, you know, it's not a big deal, but humor me, at least in my class. Fill in all the significant digits. So they do this in a number of cases. Down here in the R square, it's 0.11. Down here, it's 0.1. Is that 0.10? Is that 0.14? So, sorry, I'll stop. I'll stop ranting on about that. But I'll rant about something else. So here's the squared term issue and why they have to have this times 1,000, right? If you just did this coefficient in this format, the 0.021 oversight it, it's exactly it's not this. if you look at the table closely, it's really minus 0.00021, and the standard error is 0.000002. Right? That's often the case when you have a quadratic because you're squaring variables. So they face the dilemma of how to actually present that in this table. You know, it's totally unhelpful to have 0, 0, 0 with a standard error of 0, 0, 0, right? People put that in tables all the time and it drives me crazy. That's completely uninformative. If it's 0, 0, 0 and a standard error of 0.000. Now that could be an enormously significant variable, but you don't know because the scale is such that you don't know what the standard error is, you don't know what the coefficient is. Now think about our first day of class. We had education is some function of income, 0.14 times family income, with a standard error of 0.03. But that was with income scaled in tens of thousands of dollars, right? This is in income in tens of thousands of dollars. If it were income scaled in dollars.
Professor Duncan, I just want you to know that you're extremely small on our screen because you're still sharing your computer screen.
Oh. Sorry.
It's okay.
But you can hear my voice ranting, right? Okay, sorry. This was the equation. Education is some stuff plus 0.14 family income with a standard error of 0.03. If we were to have presented it in dollars, to scale the income variable in dollars, it would have been education equals A plus 0.000014 family income with the standard error of 0.000003. You know, that would have been completely correct, but it just would not have been very easy to understand. And had we truncated it to 3 decimal places, it would have been 0, 0, 0 over 0, 0, 0. So not only make your variable names very clear on the table, but think about, if necessary, converting your coefficients to numbers that people can actually understand. And in this case, it was fairly easy to do by just transforming the income variable before we ran the regression, making clear that this was income in tens of thousands of dollars. But with Levitt and Fryer, what they do is have this, you know, I don't think everyone kind of picked up on what this actually meant. It's not very clear. They're presenting a number that is 1,000 times bigger than what it really was. So that's why they have this times 1,000. And that's why 0.021 is really 0.00021, and the standard error of 0.002 is really 0.00002. All for the sake of producing 3 significant digits that aren't 0 and that you can manipulate. All right.
Sorry, Professor, I had another question. I don't want to like spend too much time here, but
Oop, you're cutting out. Sorry, maybe
When
you should
books
turn your video off. I didn't hear the question. You were cutting out.
Oh, I'm sorry. Am I having?
Now
Okay,
you're okay. Yeah, try again.
Can you hear me now? I'm sorry.
I can hear you now. Yeah, please.
My apologies, my internet sucks. Yes, so I was asking about this idea that when bugs equals 0, the slope is just the coefficient, so that'd be 1, because of given the formula for the slope. But is that a different conception than going from 0 to 1, which I know is change, but it just feels like the slope at a 1 might be different, so it could still be like a different. I guess I'm thinking about how that's different from going from 0 to 1.
Yeah, that's a good question. I mean, in theory, B1 is the slope right at 0, right? And the slope is decreasing as you go along the function. So by the time you go from 0 to 1, it's a little bit, the slope isn't quite 0.006, it's a little bit less than 0.006. So in theory, that might be a problem. But the fact that the scale is, going from 0 to 142, which is the maximum, and the mean is around 60, people who did the calculation the alternative way, evaluating the formula at 1 and at 0, also got 0.06. So it's a perfectly fine approximation in this case. So it's just I was hoping to give you an easy question, but it turned out to be rather difficult for some people.
Greg, one of the students asked me if you could move the camera a little bit closer to the board. They're having trouble seeing.
Sure. Is that better?
I think so.
I get this all set up beforehand, and then when it actually goes into Zoom, it kind of gets smaller. So I should have re-optimized, but I hope that's okay. Any other questions?
Greg, I'm sorry. I feel I still am unsure about how the graph was supposed to look like.
Oh, yeah. Sorry. Yeah, that's next. That's next.
Oh, okay, sorry.
So I'd forgotten about it, but once I was on a plane and the people in front of me had been served dinner. This is back in the old days when they used to serve dinner. The people behind me had been served dinner. And the flight attendant walked by and I said, I think you missed me. And she said, oh, you're next. She had missed me, but it was a very smooth kind of transition. So height of the curve, you're next. Let's go back to, this is a very important skill to develop. And that's the test of reasonableness, right? So actually my first question on the assignment was how to interpret the minus 0.437 constant term, right? And a lot of people properly said that it relates to whites. That's the omitted group. But then they said it relates to whites controlling for other variables in the regression. Right, but so I was taught TOR, test of reasonableness. always apply a test of reasonableness when you think about something. So this minus 4.37, right? If you go up to the table of means and standard deviations, so we're talking about fall kindergarten math scores, right? And they've been standardized for the full sample. They have a 0 mean and a 1 standard deviation, a 1 unit standard deviation. So for the whole sample, you know, most of whom are whites, the mean test score is going to be 0. So when we go down to this regression table and think about interpreting this minus 4.357, that can't possibly be the typical test score for whites, right? 4 standard deviations away from the mean for a group that is the majority group in the sample. That just doesn't make any sense at all. So it can't be the case that the answer, the omitted group is whites, it's for whites with controls. That can't be right. And in fact, go back to the equation, any equation, it doesn't have to be a quadratic equation. If you want to know what the constant is, and look at this equation, well, the constant is just the value of y when all of the independent variables take on 0 values, right? Plug in 0 for x, plug in 0 for x squared, plug in 0 for all the other independent variables, then you get a. Right, so it's the number, it's the test score associated with someone. Let's go back here. For someone who is 0 months of age, weighed absolutely nothing at birth, is a male. Socioeconomic status is 0. So it's an absurd set of conditions that are associated with this minus 4.357. So, you know, remember how I said the constant, never pay attention to the constant? This is usually the reason why, because people don't really think about scaling variables so that a constant has a good interpretable value. It's a projection way beyond the sample. It's almost as though you're wondering what the test score would be, you know, for a child in a home with minus 25 books. You're projecting, here's the sample, you're projecting beyond that sample to some point on the curve far beyond the sample. So I was hoping that you would remember, first of all, that the constant is just the value of the dependent variable when all the x's are held at 0, and reinforce the idea that you shouldn't pay any attention to it because it usually doesn't make any sense. Okay, so by the same token, and this follows from the interpretation of the constant problem. Some people had, oh, where's my marker?
Yeah.
When in doubt, blame Paul. So some of you had nice quadratics, you know, with 142 peaks, but they were way the heck down here. This was 0, this is test score. So does that make sense? That would fit the data? That almost everyone is going to have a minus. Everyone, on average, people have a 0 for the test score because the test score has been standardized with the mean of 0, right? So it can't be down here. And what people were fooled by was the minus 5 point whatever it was constant, which isn't the intercept, because the constant, as we said, was a value obtained when all of the independent variables took on values of 0, right? That's, you know, that's not what the constant turns out to be. So best to, I mean, what we know so far, if you have books going from 0 to 100 to 200, 300, right? We know that this function is peaking around 142. We know this is a standardized test score. So it's going to be 0 in the sample. So I actually didn't draw things right before when I had the curve up here and scatter points here. That was where the sample was with respect to books. Where they were with respect to the test score, on average, are going to be 0. So it's going to be something that's coming from below 0, peaking at 142, and then declining. We know that at books equals 0, the slope is going to be 0.06, right? So it's going to be, it's going to look something like that. That's supposed to be peaking at 142. And if you want to know the value of test scores at the peak, just plug in B equals 142 into this Book's equation, right? And you're just getting a bunch of stuff plus 0.006 times 142 minus 0.000021 times 142 squared. And if you work that out, that ends up being A plus 0.429. All right, so whatever the mean is for everything else, we're going half a standard deviation above that to get to the peak, basically. Okay, so, you know, what's important here? What's important here is that there are quadratics out there in the world of research, and we've got to have a little bit of familiarity with them. You need to be wary of them because of the tail wagging the dog here, that you're fitting a U shape with a parabola. There's no, the regression simply has to find the best U shape, and sometimes the U shape is going to be U, sometimes it's going to be inverted U. The position is all about getting some portion of the parabola to fit well to the data that you've got. If it's theoretically appropriate to have a parabola, if theory tells you that it really would be parabolic, then by all means you should use it. If people have quadratics, now you've got the tools to figure out what the shape of the parabola is. You can look right to B2 to know whether it's inverted U or U shape. You can look to B1 to see what the slope of the parabola is, where the x variable equals 0. That's usually enough. If you want to keep going and plug in values to determine, exactly what it looks like beyond that, you can do that. But you just encounter them enough so that you have to know a few of these facts. And I would say, going back to this multi-level modeling where you've got latent growth, when you've got a latent growth model.
Greg,
Yes.
before you move to the latent growth model, John had his hand up, so I figured it's a good time to ask.
Yeah, go ahead, John.
So you said that there were some students who drew the graph to have the parabola be under the 0. So it was like kind of like what you see in the graph you have on the screen, but just a little bit lower.
It was way lower, yeah.
What could have caused a graph to look like that?
Well, I didn't draw it. You mean what would actually cause a graph to look that way?
Yes.
Oh, well, if the average value of y in the sample was -5 or -4 or -3, then the heart of the graph always has to be positioned with respect to the average of the dependent variable. So if the average of the dependent variable is -5, then the heart of the graph, the heart of the data, is going to be around -5.
Okay.
Okay, but in this case, the heart of the data is at 0 because that's the way the variables scored, the standardized score. So you're going to get a lot of sample below 0. The peak is going to be above 0, right? But then some of the curve is going to be below 0.
Thank you.
Sure. Any other questions?
One of the reasons I drew the graph mostly looking like a horizontal one was because of 2C. It said that the slope when x is 0 is 0.006. So I assumed that it would be looking like a horizontal line since the slope is so small. But I'm guessing that because it's a standardized score, 0.006 would make a bigger difference than I thought.
Yeah. Well, you're going from that point that the 006 was associated with up to a level of half a standard deviation, right? So that's some distance you have to travel. But because it's standardized, that 2/3 of the sample is going to be between +1 and -1, right? So there's not going to be a lot of, if you scale it so that this is 1 and this is -1, you're going to have an awfully flat line. If you scale it so that this is 1 and this is -1, then you're going to have a much more of a curvature. So it's really a function of how you set up the scaling more than anything else. Any other questions? So my final point about quadratics is that they show up a lot in these latent growth models. They show up because, is this still visible over here? They show up because in the aggregate, it's a test score and age. In the aggregate, test scores tend to increase at a decreasing rate. So in the aggregate, a quadratic might fit okay, but these latent growth models have components that fit whatever the function is at every individual level. And then it takes these parameters that they estimate for every individual and then uses them in the next stages, the next levels of these latent growth models. We'll talk more about this later, but be cautious when you either are asked to run or are trying to figure out results from someone who uses a latent growth model with quadratics. Because this problem that I pointed out, you can have two people with very, very similar trajectories and radically different parabolas get to those trajectories. Okay, let's take a break. Okay, so now we're switching gears here. We're talking about dummy variable interactions. Suppose we've got two groups, blacks and whites. Let's go back to the example of kids, and we're interested in the relationship between family income and completed schooling of those kids. So let's say we just have two groups, blacks and whites, in the sample, and we suspect that family income is less advantageous for blacks than it is for whites. Okay, so what does that mean? That means that if we were to just take whites and run a regression education as some linear function of income, and just take blacks and run the same regression, education as linear function of income, the hypothesis is that D1, the effective income on education, is less than B1, the effective income on education for whites. Right? That's, I say effect, it's really an association, but you get the picture here. So we really want to know, we've got two groups and we want to know whether the coefficient for one of the groups on a key variable of interest is different from, in this case, greater than the coefficient on that variable for the other group. So the best way to do this test is to pool the samples and do dummy variable interactions. All right, so this is whites only, this is blacks only. Let's combine the two samples and then estimate an equation where there's a constant, E, trying to keep the letters distinct here, plus F1 income plus F2, this is a dummy variable, 1, 0 variable for whether blacks equal 1, non-blacks equals, or whites equal 0. And then F3 times the interaction, multiplicative interaction between this 1, 0, whether black and income. Okay? So why does that give us what we want? Well, you know, as usual, whenever I see an interaction equation, I want to decompose it to see what it means. And in this case, what this means, this pooled regression for whites, we have education equals E plus F1 income plus, well, whites are going to have a 0 on whether black, so plus 0 plus, and whites are going to have a 0 on whether black times income. So from this pooled sample, E is going to be the constant for whites, and F1 is going to be the income coefficient for whites. So if you were to run this pooled regression and run these individual subsample regressions, you should get, let's forget about constants. You should get a coefficient on income for whites in the whites only regression that's identical to the main effect of income in the pooled sample. All right, you can try that and it should work out. And by the same token, for blacks, the equation is education equals E. But now you have another component to the constant term, right? All the blacks will have a 1 for this variable. So they will have F2, and F2 indicates the shifting of the constant up and down for blacks relative to whites. That's the new constant. And then you're going to have F1 plus F3 times income, right? Because we've got F1 income here, and we've got F3 times income. These are all going to be equal to 1 for the blacks. So the sample, so the kind of pooled coefficient on income for the black sample is going to be F1 plus F3. So that implies if you were to compare this subsample regression run only on blacks, you ought to get a constant term that equals E plus F2 from this equation. And you should get an income coefficient here, this D1, that's exactly the same as F1 plus F3. So why go through all this bother? Because we can just run these two separate regressions. What the bottom line here is that F3 estimates how different the income coefficient is for blacks relative to whites. And our hypothesis was that family income is less advantageous for blacks. So we hypothesize that F3 is negative, and a t-test of the F3 coefficient tests our hypothesis. All right, so we pool the sample together, we run this equation, and then we can look directly at the coefficient and the standard error on this coefficient to get a test, well, first to see what the sign of this is, whether in fact the relationship, the association between income and completed schooling is indeed less for blacks than it is for whites. F3 will tell us the direction, the magnitude of the difference, and then with the standard error, we can see exactly whether in fact that difference is significant enough, statistically significant. So we can do exactly our hypothesis test on this pooled sample, whereas when we did the separate sample, we got something for B1, we got something for D1. It's not obvious how you would do a test for the difference between those two. There are ways to do it, but this is the easiest way to do it with dummy variable interactions. Questions? They're pretty straightforward. Until if you're way ahead of me or stunned in thought observing this. Okay, I see a couple of thumbs up. I'll take that to be the universal sentiment. And just to reinforce what's going on here, if we have family income, and over here, completed schooling, completed ed, we're going to, in effect, fit these two equations, even though it's all one equation. The white equation is going to have some intercept E, and then a slope of F1, right? We said in this pooled equation, F1 is the coefficient for whites. And then blacks are allowed to be different both in their constant term. Let's say that F2, the shift is positive. So this is E plus F2. This is for whites. For blacks, we're going to have possibility of different constants. It's going to be higher or lower. In this case, we'll assume F2 is positive. And we could have a different slope too, a different slope that is differing by F3. So, suppose that it's something like that. And the slope is going to be F1 plus F3. And the F3 part of this is going to say whether these two slopes are significantly different from the other. All right, so what this functional form does is allow us to fit two lines in effect, one for each of the two groups. Okay, easy enough. So sometimes when people estimate interaction models, they include all the interactions, but they sometimes leave out the main effects. Right? So suppose you ran on a pooled sample income and then whether black times income, but left out the main effect of whether black. What would this graph look like then? Sounds like a breakout group question, doesn't it? All right, so 10 minutes. Paul's got you all set up for breakout rooms. Here we go, and he's given you some Google Sheets to show me what your graph, and the rest of the class what your graphs look like. Good. So let's pick a group to present. Let's pick group 3.
I was in group 3, and we have the original and then the equations for when we leave out the main effect.
So everybody's pulling up group 3's slide, right?
I think so. Is
Yeah, I
everybody?
just want to make sure everybody's looking at the slide. Okay, go ahead. Sorry.
Okay, so the original one for the black equation for the blacks were the constant was E plus F2. So you could see in the original graph that the constant and the y-intercept is above the whites. And then after you leave out the main effect, the only difference is that the constant for the black becomes E because we don't no longer have F2 in the equation. So the slope would be the same, and the line just comes down towards where the intercept for the whites are.
That is exactly right. Does everyone see why it's right? You're really introducing an additional constraint that wasn't present when you had the main effect in there. You're forcing the two lines to pass through the across the y-axis at exactly the same point, right? Instead of allowing them to be different. Over here, we allowed them to be different. So that constraint doesn't make any sense, right? It doesn't make any sense for the value of completed education to be identical for family income equals 0. So you're really going to force, if you've got flexibility, you're allowing these lines to each fit their own subset of the data in the way that minimizes sum of squares. But if you're forcing both lines to go through any particular point, then you can't be fitting things as well. You can't be getting a slope for the blacks that's right, because the right slope is here, and you're forcing this line to go through this common point. So leaving out the main effect, which people do sometimes, they're so eager to put the interaction in, they sometimes forget to include the main effect. That's not going to give you the right number for the difference in slopes between the two different groups. So always have all the main effects and all the interactions in there. I was starting to write up what happens when you've got more than 2 groups, white, blacks, and Hispanics. I probably don't even need to go through all this. You want the income coefficient, you want a main effect for blacks, you want a main effect for Hispanics, you want an interaction term for black times income, and an interaction term for Hispanics times income. Right, so you want all of these interactions together in order for you, in this case, to estimate 3 lines and to be able to test whether the slope, and we don't care that much about the constants, we want them to be flexible and take on whatever value they should to get a best fit. But the main focus is on whether this coefficient B4 is significantly different, right? Because that tells you whether the payoff to income is significantly different for blacks relative to the omitted group of whites, and B5, whether the payoff to income is significantly different for Hispanics relative to whites. You could, if you wanted to test whether the effects were different between blacks and Hispanics, you could do this test for whether coefficient on black times income equals the coefficient on Hispanic times income. And so that would tell you whether the slopes are different for blacks and Hispanics. You could also test whether collectively black times income equals Hispanic times income equals 0. So that would tell you whether either blacks or whites, or taken together, whether there are any subgroup differences at all, right? If there's no significant difference across the groups, then you can't reject this null hypothesis. And that's what the test is going to give you. This, on the other hand, is just going to tell you whether these two things are different. They might not be different, but they might both be different from whites. So you can have all those combinations. Okay. So any questions about that? Just have to kind of play around with this, which you'll do in the problem set this week, right? And the problem set includes what are called fully saturated models. If in general you've got a bunch of interaction terms, we typically have some y equals a plus b1 x1 plus b2 x2 plus b3 x3. You can, that's the main effect model. You can have all sorts of interactions. You can have interaction between x1 and x2. You can have interaction between x1 and x3. You can have an interaction between x2 and x3. That's called a fully saturated model, where you've got everything interacting with everything else, right? And I don't know if I've ever estimated a fully saturated model myself, but once you start thinking of interactions, some people kind of go crazy and imagine every possible interaction there is. But you can just multiply up new variables for whatever interaction you want to test and throw it in.
Greg, is a fully saturated model the same as a fully interacted model?
Yes.
Okay, great. The reading said fully interacted model.
Yeah, sorry, yeah.
Okay.
Same thing.
Cool. Thank you.
I think in SEM, there's another meaning of fully saturated, but in terms of interactions, same thing. All right. Well, the good news is that's the end of class. The bad news is that there's still a 40+ minute lecture to look over on moderation versus mediation. So take a look at that during the week. And I'll have my office hours this Friday at 11 if people want to join me to ask questions. Other than that, see you soon.